hit record. We can start going on the clock here. So, well, welcome everybody. This is the first of several workshops that are going to be on the seismic Wavefields initiative that Iris is leading. So, if this is your first go-to meeting, I hope it goes smoothly and that we don't turn you off to the forum. The way this is going to work is that as people are coming in here, and I've seen a couple more people join, you want to mute yourself. And you can do that by, we want to check and make sure that your audio is okay or that you're confident in that. And then you want to hit this icon at the top left of your GoToMeeting panel, which is going to allow you to self-mute. If you're on a phone dialing in, you just want to hit mute on the phone. And the reason for that is we want to have a broad discussion that's ranging, but we want to make sure that we don't all run out of the room because there's audio feedback on several mics at once, because that'll make it pretty unpleasant. So if you're here, that's great. We'll go through all the presentations and just try to be cognizant of all times of whether or not you're muted, because that's an easy thing to lose track of. And it's really important for a meeting like this with almost 20 people in it to be a pleasant experience. So I think that's all I'm going to say. If there's somebody who's making noise, I may but not speaking, I may make sure that you're muted, and I may try to communicate with people individually through the chat window, which is at the bottom here. And vice versa, if you have any questions or problems on your end, send me a note through this chat box. That's a way to communicate without interrupting the rest of the conversation. So, all right, I think that's all I need to say. And to whom shall I give screen sharing for first?
Greg told me that Jamie will control the slides. Is that correct, Jamie?
Yeah, I'm ready to go.
All right, here it comes, Jamie.
All right. Somebody want to hit full screen with that or control that? That'd be great. Should I go ahead, Greg?
That look all right for everybody?
Yeah, John, go ahead.
All right. I'm John Hole of Virginia Tech, and together with Bob Woodward at IRIS, who's on the line, we are hosting a workshop series that we're calling Recording the Full Seismic Wave Field. And I think the philosophy of that is showing up here on your screen with these icons, that the goal is to record full wave fields, not just waveforms, to reduce spatial aliasing and aim for resolution. Next slide, please, Jamie. Probably most of you are familiar with the idea that we're actually doing this at a few scales. At the US array scale, we've managed at the hundreds of kilometers and tens of seconds to record full wave field, and probably everybody has seen these wonderful movies going across portions, or in this case, by looking at several earthquakes across the entire United States. We're doing it at tens of seconds. And at the very, very much smaller scale, industry, Nodal Seismic, and Dan Hollis is on the line with us, has the capability of putting out thousands of stations and doing the same thing at hundreds of meters and tens of hertz scale. Next slide, please. And what IRIS has been thinking, inspired by these sorts of applications, is that we'd like to prepare the community for the capability of doing such at all scales. The advantages of full wave fields are pretty strong. And therefore, there's several simultaneous activities going on within IRIS to try to move forward with this activity. The first is there's been a series of workshops and some investigations with the manufacturers to try to identify what the technologies are out there and to inspire the manufacturers to perhaps put them together and improve methods. I don't want to talk in detail about what those technologies that we're seeing are, but suffice it to say that there's some very strong evidence right now that existing technology or imminently packaged technology is going to enable us to move in some new science directions, primarily by significantly reducing the cost per station and the effort of deploying each station. And this is where the capability of potentially putting out hundreds or even thousands of instruments lies. Now, in order to get funding to produce such a facility, IRIS also needs to enunciate the science need, and that's why we're holding these workshops. Simultaneous with this, realizing that NSF is not likely to be able to fund the full cost of such a thing, IRIS is starting to build some partnerships, in particular with industry, Department of Defense, Department of Energy, USGS, AID, and so on. And if there's other people that we should be talking to, absolutely please help us to get them as part of the conversation. And you've probably also heard, quasi-independent of that, that there's several initiatives within IRIS that are being created. One of those is large N, which is kind of what we're talking about today. Another is global arrays or the seismogenic zone. And I can imagine where other next best things, next big things, sorry, might be enabled by having such a facility. So again, next slide, please. To look just a little bit at some data, here's a coincident recordings using broadband seismometers and active source seismometers looking at the same earthquake on the other side of the planet. So these are recordings of coincident arrays in Idaho and Oregon. And on the left, you can see with the broadband seismometers that we're recording really high quality waveforms, but even at 15 kilometers spacing, we're aliasing at somewhere around 10 seconds. On the right-hand side, we're recording really, really high quality wave fields with the Texan instruments at a couple 100-meter spacing, but only mediocre waveforms because these are 4.5 hertz phones, and the record you're looking at is 1 to 10 seconds. And the idea is that the new technologies will enable us to combine the best of both of these worlds. Next slide, please. So the philosophy behind all of this is that the improving technology will enable new science. If we can get our hands on a set of new instruments or a new facility that is simpler to use, less expensive, it could enable us to record well-sampled wave fields. And if we can do that, we can pull online a whole series of brand new wave field imaging and analysis methods that are simply not possible when our wave fields are aliased. The goal here is that we can improve the resolution of the source and the resolution of the Earth model, allowing us to do new science. Next slide. So the goals of this workshop series are, very plain and simple, to establish the science that could be enabled by full wave field seismic data. Our goal here is to use the results from this series of workshops. Today is the first of those workshops, and we're talking today about earthquake sources and earthquake hazards. But there's going to be a series of workshops on other applications from global to environmental scale. And the goal is to compile these together into a document, a glossy document, some slides, poster, websites, and other materials that we can then use to talk to funding agencies to try to make this a reality. We have a pretty limited time today, so Greg and Jamie are going to be hosting this workshop focusing on this specific problem of the earthquakes and earthquake hazards. And we should not be talking about the instrument specs per se. We do need that information, and we may get back to you and ask you to help us establish what that needs to be. But today, with our limited time, we should be focusing on why we should establish such a facility, not what precisely should that facility look like. The why should be driving what we're doing. So within that framework, IRIS hopes to gather this document over the course of the summer. Jamie and Greg will be compiling the results of this workshop and other people compiling other workshops. I'll be helping to edit this document and to produce this information over the course of the summer such that we can then start going forward with the partners and to our funding agencies to try to figure out how to make such a thing happen. So before I hand you off to Jamie and Greg, I'd just like to say, hey, is there anybody with questions as to what is IRIS thinking about all this? I can certainly help to clarify that, and then we should get on with what is the science that we could do with such a thing. Questions?
John, maybe you could say, this is Greg, maybe you could say something about how many other workshops there are and what sort of topics they cover, because it's very broad.
Absolutely. There's going to be a workshop on global seismology, on broadband regional seismology, on active source seismology, on source discrimination and CTBT applications. There was a workshop last fall on the ocean community, and we're going to use the results from that workshop. It's possible the source discrimination one might be taking advantage of a workshop going on next month, so I'm not quite sure whether that'll be online or at that face-to-face meeting. And on polar and on volcanoes. And if people think about some other application that we've forgotten and really need to get to, absolutely talk to us and we can try to organize that as well.
Okay, so thanks for that. So that sort of it gives you a sense for how broad this initiative could be, and in order to we have to make a compelling case for the science that would be enabled through studying the earthquake source, say, because in some sense that interest is competing with these other interests. There's obviously overlaps and synergies, but there's some specs that we might need that might not be so important to other communities.
Yes, the goal here is that we'll produce a science case for all applications while recognizing that it will probably not be a single instrument that meets all needs. And ideally, IRIS would want to support all of these communities. That is the goal here. Now, clearly, there's going to have to be some instrument gets purchased first, and perhaps one community will benefit before another. But the goal here is to absolutely support all of the communities over the long haul.
Yeah, good point. Okay. So with that, if there are no questions, perhaps we can get started with the presentations.
I didn't see, Rob, are you online?
Rob is here, but I don't think he has any sort of audio connection, and I haven't
do through
heard.
the phone now. The audio doesn't seem to be coming through to my Mac.
Okay, great. So there's Rob.
Okay, perfect. I'm going to go to full screen mode, and then just let me know as you want me to change the slides there.
Are you asking me to talk?
Yes, sorry. Go. You're up. The slides are up. Are you able to see them?
Yeah, can you go back one? You're on the last slide.
Oh, sorry. There you go.
Okay, so I didn't hear your preamble. I'm sorry. I just figured out my audio in the last couple of minutes. So anyway, presented in the next two slides are the things we're working on regarding the source using the Long Beach data. And on the upper left is the array, which I think a number of you have seen. But for us, the important thing is that this area is crossed by the Newport-Inglewood Fault, which is a fairly inert fault in that it doesn't produce much active seismicity these days. But of course, it is the origin of the 1933 Long Beach earthquake, so it is capable of a 6+ earthquake. On the upper right are one of the Wavefields that we observed from a little earthquake off to the left of us, showing that there is quite a bit of structure in there, as indicated by the tear up of the Wavefield as it crosses the fault. And further on the right side of that panel is a attempt to make a microzonation map. That is, as that earthquake passes all of the sensors, we capture the acceleration, the maximum acceleration that each sensor got, and that's what's plotted there. We scale out of that plot the 1/r distance dependence, and in theory, if everything were homogeneous underground, that would simply be a map of the shaking you would see on the surface. When we look at that from a number of earthquakes, and I'm only showing one here, is that pattern changes. Some parts remain the same, but it changes. It indicates to me that the structure is coming from some depth. And so what we're trying to do now is to figure out if we can explain this kind of rapid change in acceleration pattern. And I'll point out it's a factor of 5 across this rather small area. By looking at structure, and here's the first attempt by Fan-Chi Lin, is looking at surface waves created by ambient noise correlation with the data on here. And you can see that we have some shallow structure in there, in particular the slice at the depth of about, I think, 600 meters indicates the presence of probably the Newport-Inglewood Fault itself and perhaps an old channel of the Los Angeles River. And so this indicates some level of hazard, and immediately to the right of that you can see some cross sections that indicate some of the variation. But clearly this structure is not going to explain the panel in the upper right, and so we need to look deeper. And so that's one of the things that we are pursuing, is to try and match the structure we see with something that's there. So can we predict these accelerations we see from a structure? And then the second half of this project is to use the data that's recorded on this array to actually back project and see if we can find the micro tremors that are occurring in this region, or in particular on the Newport-Inglewood Fault. And in the lower right, you can see an attempt to do that in a fairly simple way, where we define the fault as a simple planar structure and back project the energy onto it. And you can see that we are getting some activity. There's clearly streaking, probably related to some artifacts of the back projection, but we are getting focusing of energy. The right little collection of panels shows just a few snapshots out of a 600-second run, and the one that's embedded into the little mesh there shows one sample of that and one little earthquake, the little white star that we were able to locate. And when you look at this, as you look at it as a movie, it looks like a summer thunderstorm. It's chattering everywhere, and this may very well be the phenomena that we notice on these somewhat inert faults, that the way they between big earthquakes is what they're doing. And the next slide is an attempt to do that in a little bit more sophisticated way, where now we back project into the volume. So we create X, Y, Z positions from the surface data, and you can see one slice of that. And one of the things that we have noticed, and it matches the seismicity, the energy is showing up deeper in the sort of 12 to 20 kind of kilometer depth. And you can see that it's staying fairly close to the fault. The white diagonal line is the nominal Newport-Inglewood fault. One of the things that concerns us with this is whether we're simply projecting surface noise downwards. And one of the things that sometimes indicates that that might be the case is if you just look at the spectrum, the temporal spectrum of the images we get, there tends to be a variation that corresponds to the two solar tides. And this is troublesome because that's also where artificial energy lies too. So we're working on that, and in particular we're learning how to divide the surface up into subarrays to do horizontal energy cancellation, and we're now working on trying to take the data and downward continuing it to, say, the midpoint halfway down at 10 kilometers, thinking that at 10 kilometers down the surface is as far away as the earthquakes are beneath us, and maybe we've canceled out a significant portion of that energy. So this is work ongoing, but it clearly depends on the density of the data to make this work. We unfortunately are in the middle of an urban area, so we have to deal with the problem, but I think with this density we might be able to say something about what the micro-slip history is on these faults when they aren't actually creating earthquakes, or even earthquakes that are detectable by the Southern California network. I will point out that in this area, and it's on the, there's one station from the Southern California network, and the next station is probably 10 kilometers away from here. So that's a summary of our results, our work.
Great, thanks, Rob. That's really interesting stuff. So the it's a combination of ground motion prediction, sort of shallow structure imaging, and this continuous back projection for really earthquake detection. I was wondering about the ground motion variability. If you go back to slide 1, you said there's a factor of 5 variation in amplification, I guess it was.
Yeah.
And so those sensors, are they individually calibrated, or are you assuming some nominal response? How does that work?
So to do this, we assume that they are all approximately equal, and these are high-quality geophones in them. They're, of course, velocity sensors, so we differentiate the signal to create acceleration. And then to calibrate them against acceleration, there's you may notice in the upper left plot, in the white, the red dot thing showing the array, there's a little station called STS. That's one of our broadband stations that has a real calibrated accelerometer at it. So we calibrated the nearest clump stations to that accelerometer, and then used that calibration over the whole array.
Yeah, I wanted to add that, you know, even if you don't do the mapping to the structure, just characterizing the variability is really important, because the ground motion modeling community, the people who construct ground motion prediction equations, the predictions they get are typically log normally distributed. So a little sigma in sort of log space goes a long way in hazard. So it's really important to get constraints on that. And typically, as you know, we have very sparse recording. It's hard to do.
I also think that there's a case to be made that a lot of the damage we see from earthquakes is, of course, due to variability of construction styles and quality, but I also think it's due to variability of the acceleration, too.
I'm sure you're right. Other comments or questions?
I'll just...
Can I ask a question, too? Oh.
Go ahead.
Well, this is John Vidal. I guess my comment would be that if you can really see humming faults like that lower right diagram, if I'm understanding this right, that would be kind of a revolution, a way to find slowly moving faults just by looking where the noise is coming from. I guess I'd like to see more convincing evidence. Is there some really good evidence that proves this is coming from deep in the earth?
Well, John, that's exactly what we're working on now. We feel if we write a paper, there will be reviewers out there like you, and we need to address their issues.
Yeah, because I've heard claims like this for a while, and it really would be exciting if it's true.
That's right. And so we are working in a noisy and urban environment, and we need to learn how to take care of that noise. And it's not something that I'm used to doing, and I have not. We're working on a number of techniques.
But we could go to a quieter place and put out dense, 1D lines and pick up the faint signals without knowing exactly where they're. There are easier ways to do this, perhaps.
Yeah, but if you put out a 1D line, then you're presuming that the energy's on the fault. I'm not presuming at this point that the energy's on the fault. And in fact, I will point out some structural things we've done other than what I'm showing here. We're not sure where the fault is at depth.
Right, but 1D a crossing line, for example, would take a lot less stations with that kind of density and give some location estimate. But anyway, it seems like something worth pursuing.
Well, yeah.
Other questions or comments?
This is Ralph. Rob, can you tell me whether or not that most of the hum or what you see for the noise is coming deeper than what they would normally project to be, let's say, the microseismicity on the Newport Inglewood?
Well, the seismicity here, and I believe Ailes in the group, he can correct me on this, but it's deep, meaning that it's in there's events down here in nearby regions that are down to 20 kilometers. And so most of the seismicity we seem to see comes from the 10 to 20 kilometer range here.
Okay.
Okay, great. Well, thanks, Rob, for getting us off to such a fine start. Jamie, who's next? Igor.
Sorry, I was muted there. Igor is up next.
Okay, hello. Can you hear me?
Yep.
Okay, hi, I'm Igor Stobailo and from UCLA. I will be touch basing basically not the data collection itself, but the data delivery, and mainly it was implemented by telemetry. And what you see on the slide right now is a snapshot of our recent Peruvian deployment, and on the map you can see sites in a roughly square shape, and the red line was mainly wireless sites and black was standalone classic sites. And the way it was implemented, we had broadband stations on all 50 sites and roughly covering 300-kilometer lanes from the coast to Lake Titicaca. Approximately between like stations, the distance was maybe 6 to 10 kilometers. And we tried to deliver the data as fast as we could. Basically, on the next slide, you will see how the path of the data was done. But essentially, if you're talking about the telemetry, you having much more ability to deliver the data right away and to do much more than with standalone stations, because you can you have a real-time feedback and you have real-time control of every station. But if you're going, the telemetry path and you want to implement the wireless data delivery, the planning and installation time takes much more, obviously. And you start basically with site selection, and you can see on the slide, it's basically the field for us that first you have to select the sites for wireless delivery. And the problem with wireless, especially Wi-Fi that we used in the field, that you have to have a line of sight, and you have to pick the sites where every site can see the other site in order to deliver the data. So the sites themselves, they were, standalone sites with wireless and, more or less secure locations, and we had solar panels at every site, so it was autonomous as far as power goes. But every site has an antenna pointing in one or two antennas pointing two directions, as you can see on the lower left picture. So if you, next slide, please. So here's I put the pros and cons of wireless, and at the top you can see how the data basically is delivered for the large scale installation. So you in the current picture, that what you see, it's mainly it's suitable to detect large tectonic structures. It's not for the urban areas. That I will talk about it in the next slide. And the data delivered is wireless from hop to hop mainly, and until it gets to the computer that is connected to the internet. And on the way, if you look at the station topology, it looks linear, but if you track the path of the wireless, how it travels from side to side, it's not even close to linear, because if you have hills, you have to go around them. If you have tall structures, you have to go around them. So if you look at the path propagation of the wireless signal, it basically goes every each way. And if you want to connect all the sides properly, you have to have a number of repeaters. Basically, the sides that would be having 2 or 3 antennas that would connect the sides with sensors, but repeaters would not sometimes collect any data. They would just transfer the signal. So there is a definite complexity in the wireless site selection and installation. And as far as pros goes, obviously you have a real-time data analysis, because we were collecting data every day, and if earthquake happened yesterday, you have the data today, you can process right away. And you can redesign the array based on the science fairly, easily. You can obviously have can implement early warning. That's how Japan, for example, is doing with wireless and wired data delivery. It's the time delay is fairly low, especially if you design it properly. You can have a quality control, and this part is quite important, because if you collect the data from standalone sites, you, let's say, collect the data from the field once a month. If your sensor is locked or is not functioning properly, or the cable is bad, you don't see it right away. With wireless, you can see immediately, and we had the tool set that would look at the data quality as far as seismic data goes and the wireless connection quality, and we could see the problem right away. We could see, because we had used Duralp 3T active sensors, and those need to be centered and locked and locked. And if one of the channels is bad, you could see right away. And especially in Peru, you cannot fix it yourself right immediately, but we had people, local people helping us up there, and we could ask those people to basically go to a particular site and fix it, because we know there is a problem. And the longest link that we had with wireless was approximately 40 kilometers, and that's we used the radio from your regular laptop. Basically, how to achieve the 40 kilometers, you have to have a really nice line of sight, and we had parabolic antennas, we had some amplifiers. So as far as the distance, if you have a nice clear view, you can achieve very good distance, and the velocity was the speed of delivery was quite good. Especially, if you talking about Peru, they have mountains. We went through the Andes, and if you install antennas on top of the mountain hills, you can cover a lot of territory. As far as the cost, that's not very obvious, but the overall cost, if the wireless works well, it's lower, but initial cost it might be higher because of the permissions, because of the antennas, because of the site selection, which might be not easy to do. So this would be the first point on the con side, on the right side, that the time to set up is quite long, especially if you like to have sites that, let's say, have TV towers or radio towers. You have to get permissions from the proper parties to install your site and antenna on that area. Usually with standalones, you can just go to the house, you like the location, you talk to the owner, you dig a hole in the backyard, and you're done. With telemetry, you have to make sure that you can see the other side, and your site is sort of high in the ground, so it's much more time consuming. But at the end, if you know, it may give you a lot of benefits. And the one thing that we came up, not came up, but we found that if you go wireless, you have to have people who understand how to debug them, how to set up the wireless properly. The people basically that have computer science background. If you just ask a regular seismology student to install a standalone site, it's mainly digging, you know, unlocking, and you know, making sure the data collection is done, and it can be done with some devices. With wireless, you have to have, in our case, Linux knowledge, and because data collection boxes, we're getting data from Quanteras and collecting data on compact flash cards and sending data with wireless and so on. And the system was system knowledge was very important, because if something doesn't work, you have to know how to debug it. And this is quite could be a challenge if you don't have a proper stuff, for example. As far as the data, sort of the topology, you have to have a pretty good and lengthy sort of planning for to choose the proper sites, because the way we've done it, we basically drive around the road, and the first time you drive, you select, let's say, 3 times more sites, and then you go again and see how they can see each other, and then you talk to the owners and see which ones allow you to put the station on the ground. And it's basically site time selection. It's quite long, but at the end it pays off. As far as power hungry, that I have this point, but if you have a small standalone site without wireless, it may take, let's say, 1 watt power approximately, and the small solar panel and small battery might suffice. But with wireless, the wireless component takes more power sometimes than the seismic component. And what I mean is that, for example, the radio we had was a 500 milliwatt radio itself, and if you add amplifier, if you're talking about long link, it might be, let's say, 1 or 2 watt amplifier. So you're talking about, let's say, 3 watt wireless component itself, where you know, just standalone would be, let's say, 1 watt. So you have to plan as far as power goes. It means larger solar panel. If you know, you're talking about really remote areas, it might be you know, beneficial to have this site with more batteries, more solar, but it might be difficult to install sometimes. And in case of wireless, if your link is weak in terms of bandwidth, you may choose to transmit the events only, not the complete data sets. But the complete data set might be collected on the compact flash or hard drive locally, and you can pick it up later. So it's sort of like maybe designed as a mix, delivering events and collecting data on site, or you can, in our case, we transmit complete all data.
Igor, we've got a lot of people in line to talk, and we need to...
just one more slide, and that's it. So please next, and I will be done. Yeah, as far as you know, just want to mention that we covered the remote installation areas, sort of Peru 300 kilometers. But before you start wireless, you have to select. You have to decide if you're gonna do urban, sort of populated area, or remote installation. In our case, it was remote installation. With the populated urban areas, you can come up sort of. We decided. I put this diagram in the lower left, that probably you would have a mix of wireless delivery, where you would have cell towers, you would have satellite delivery and Wi-Fi, and mix of sensors that would allow you to achieve your science goals. And the sensors could be different. Broadband, very few, and geophones, many more geophones. And as alternative, I put sort of, since you're talking about wireless, the wireless nodal seismic setup that they have, that, as Rob mentioned on the previous slide, a lot of sensors that would just collect the data locally and would be very easy and simple to install. And I guess I would stop it here and would take questions. Thank you.
Okay, thank you. So questions or comments? So Igor focused on the sort of technical aspects of it rather than the science, but that I think the latency and the difficulty of getting data into a data center rapidly and making sure it's high quality, that sort of supports all the scientific goals. That if something doesn't get into the main processing stream in, say, the Southern California Seismic Network, it's very hard to go back, and it takes special effort to go back. And
yeah, all data is stored locally. So if something is not delivered over wireless because, let's say, wireless link is broken, you can pick it up later as if it's a regular standalone site. So the data delivery is done from every site as it's possible. If it's not possible, you can collect the data, later on. So you're not losing data, by any means. Yep. The wireless delivery just allows you to process data as it comes in immediately. And if you have remote areas with events that you would like to process right away, that allows you to do so.
So I think this is Jamie. I just I think maybe what we need to take away from this is what is the science that requires the continuous telemetry of data versus, if I'm not mistaken, all of the Long Beach stuff is done post recovery of the instruments or of the flash on the instrument, and so that's all science that can be done without having real-time telemetry. When you get into earthquake hazards and things like making shake maps or doing real-time source investigations as an event unfolds or quickly after an event, you can't do that unless the data is coming in. But I think we need to probably come up with some recommendations as to what are the requirements for, because it's going to add a lot of cost and may not be possible to bring in thousands of channels at a high sample rate into one data center. So anyway, just something for people to think about, and if you have comments, maybe email them to Greg and I. I don't know if we want to spend a lot of time right now. We've got a lot of other people who want to talk, but I certainly would be interested in people's comments on that.
Great. That's a excellent sentiment, Jamie, and recommendation. So why don't we move on to the next presentation? So who's next? Maureen. Maureen, are you there?
Yes. Is it working? Can you hear me?
Yep.
Okay, perfect. I think this is the last slide.
Sorry,
okay.
Does that look good?
Yeah, it's perfect. So I've been working, we have been working with some networks in Japan and trying to combine two dense areas. So in this map I'm showing the black triangles are the HiNet stations, and so this is map of Japan and Honshu, and I'm using only 400, so half of the seismic network. And the yellow triangles are the mesonet stations. So this is a really dense seismic network. The spacing between those stations is about 2 kilometers, focused on Tokyo and the Kento Basin in particular. So this is an urban environment. As you can imagine, Japanese cities are really developed. And they installed shallow boreholes about 10 to 20 meters deep, 3-component accelerometers. And I've been combining those with the HiNet stations, which are deeper boreholes, I think about 100 to 200 meters, and velocimeters, and also 3 components. So can we go to next slide, please? Okay. And so there's a few animation missing here, but the bottom line is that I've been trying to characterize wave propagation in a very deep sedimentary basin. And because of the density of this network, we've been allowed to look at how the move out, basically, of the main phases that we see traveling from a virtual source that could be a seismic station, which is, for instance, the red triangle here is the HiNet station. And then with the correlation technique, we look at the Green's functions. So the Green's functions are correlation in time of continuously recording of the ambient seismic field. And supposedly what you get out of this is how the waves will propagate from one point, let's say that red triangle station, to all the receivers in Kento. So the geology is fairly complex here. We have a deep sedimentary basin. Because of that, in terms of the seismic hazard, you have enhanced ground motion as wave pass through that structure. So those sensors are 200 hertz sampling rate. So it's a bit, it's a lot of data, and I've been trying to downsample because I'm mostly interested in the 1 second to 10 seconds ground motion. So we see on the left wiggles, you see there's a positive and negative time. This is the symmetry that you should expect from the reciprocity of the Green's function. There is some asymmetry that you know, you can ask me a question about later, but this is what you see on the negative times. The top left corner is as if the source was there, so distance 0 kilometers. And as you move down, you see how the waves propagate away from the source. So I highlighted a few move outs as we see the waves propagating from the top to the bottom. So they move away from the source, they cross the basin, and we see very complex waveform that we have yet to understand, but we see very slow phases, possibly body waves and surface waves that are really, really slow when we think about you know, waves traveling through the Earth. This is about sound speed, very soft sediments. And you can see also dispersion of the phase, which shows the extended duration of shaking, which is a hazard for buildings. On the right panel, you see also move out from a station that is located on the eastern side of the basin, HSNH. And again, we're trying to map how the waves propagate from that source to the receivers in the basin. I highlighted again some of the move outs of the phases, and we can see faster wave speed, probably multipathing, and reflected waves, possibly from a very complex basin structure. And again, we see reflected waves that something we could not see with less dense areas, basically, as we map those move outs. Next slide, please. Okay, so this is going to be an animation, and it's always changing to make them work. But what I'm going to show here is, because we have these 3 components, and this is, you know, very important to look at the 3D wave field and not only the vertical components. The horizontal components tend to have a very enhanced ground motion in sediment structures, and because of that, we're interested in looking at what's the shaking for horizontal components, and not really knowing the phases we have, I just, you know, looked at the polarization of the waves and trying to discern between Rayleigh and love waves. And so I'm going to show, as the movies goes along, hopefully, what the polarization of the phase in horizontal ground motion. So if it's a vertical force, we should expect only Rayleigh waves, and those would be polarized perpendicular to the wavefront. And love waves that will appear because of the complex sediment structure will be polarized parallel to the wavefront. I don't know if you can play the movie. Is it Jamie? It should be linked because I sent it, so I hope that, yeah, that's gonna work. Okay. All right, so the source is on the east of the basin. It's a very shallow dipping sedimentary structure there. Can you click on the? I think just if you click space, it should play it.
Sorry, did you say click what? Click
space.
Click.
Like just on.
There we go.
Okay, so here we go. So the waves are traveling, and you see the. It's kind of messy, but there's like definitely Rayleigh waves coming out that travel faster than the secondary phase that we see on the dark polarized parallel to the wavefront phase, and that's supposedly you know, it's polarized as a love waves. So in theory, in the 1D Earth, you should not see love waves excited like this, but because of the density of this network, we've been able to map this for a fairly complex basin structure. And the shaking goes for 300 seconds, which is extremely long and great to map as a in terms of hazard. So there is a lot of complexity here, and I hope to unravel this later on in my postdoc. Thank you. Can we go back to the slides, please? For the last slide. So the other thing that happened, sorry, somebody's calling. The other thing that happened is not only how we see how the waves propagate and how the enhanced ground motion is going, but we also see with the 3D wave field complexity in how those waves that we are trying to extract are excited. And here I'm showing on the left panel the vertical to vertical Green's function from one source to all the receivers. You see there's a lot of complexity that only dense seismic network can actually show, where you see probably diffracted waves, multipathing, and all that going on. But on the other hand, I'm showing on the right what should be the love waves component, and you see that there's like a symmetry of the Green's function that we do not see for radio waves. So it's not only about the hazards, the ground motion prediction that we could also see from this seismic network, is also what are the phases that we're trying to get out of that, and where do they come from, and trying to understand more like the origin of the microseismic wave field. And that's all I have for today.
Okay, thanks, Marie. So that makes an interesting comparison with the nodal seismic array in southern part of Los Angeles Basin, in that your station spacing is about an order of magnitude larger, 1 to 2 kilometers. You're looking at longer periods, longer propagation distance, something like 1 to 10 second period, maybe 2 to 10 second. It's 3 component, and it's also borehole. So it's, there's some similarities and some differences and advantages. So comments, questions?
And I've got a comment or question or two. I mean, yeah, this looks really great. I mean, these basin responses are hard to unravel, and these data sets are showing us a lot of things. But I guess it's not clear this is an alias data set. I mean, a lot of these waves are short wavelength, especially with the slow velocities. And I guess there's an issue of, where you have to go from deterministic to statistical descriptions of the wave propagation. I suspect the fine scale structure may not matter so much for hazard, but getting the longer period basin resonances may matter more. Do you have some ideas of how to focus this to aim at particular problems?
So I actually think there is aliasing going on here, because the sediments have about 500 meters per second shear wave speed. So it's actually not dense enough for the sediments we have. I've been looking also at the large, long period ground motion basin resonance, and the Green's function we get out of this study actually have pretty coherent signal within the basin resonance that we find about 4 to 5 seconds. But there is strong variability in, I would say, shallow crystal structure in terms of ground motion, and I think looking at the statistical way would be interesting, because if you look at where the virtual source is located in Japan, the actual ground motion that you can predict, the peak ground motion, is really, really different due to the structure. And so I think by looking at, if you take all the high-net station as sources, you can start looking at statistics on ground motion because of variability in the crystal structure around it. So this is a really large data set, so it has its challenges.
And also, I guess you need to leave instruments out a long time if you wanted Green's functions between sort of distant points at high frequency. I mean, doesn't there take a lot of stacking to get that signal?
Oh yeah, I strongly agree. But this Mesonet has been deployed since 2009, and it's continuously besides when Tohoku hit, where it had a 1 month shortage of power, but it has been continuously recording since then. I have been working with 4 to 5 months of stacking, which is pretty minimal for 300 kilometer spacing. It's actually very high quality data.
Can you put out more denser stations and stack across stations as well as across time? Would that make the studies easier to
Yes.
do in a short time?
Yeah, so what you can also do is use asynchronous deployments and use permanent station to bridge networks together and basically make a virtual denser network. And I'm going to be working on that pretty soon for Northern California.
Yeah, this is great. We're trying to think of how to use it in the Seattle area.
Great.
Okay,
Can I ask
other
a question?
questions? Oh,
Yes.
sorry.
This is Jigampan from Georgia Tech. I was just asking a question about the first slide. You show some interesting signals propagate at 330 meter per second.
Yes.
Could those be just like, I don't know, like infrasound signals or anything that's propagating in the air instead of in the ground?
So I think I see that at all components, so I'm not sure about, because infrasound should be a pressure wave,
Right.
and should be a scatter field. I think this is a very dispersive, so I'm not sure about the acoustic dispersion, but those waveforms are extremely dispersive. I'm pretty confident those are radio waves. So if you think about, if you had a layer of half space, for instance, the radio wave speed would be about 92% of the shear wave speed, and this kind of corresponds to what the shallowest layer would have for a radio wave speed.
All right, thank you.
Thanks.
Okay, we should probably move on. Jamie, you ready to load up the next one? Thanks, Marie.
Joe, you there?
Yeah, I actually don't see Joe.
Maybe we can move on to the next one and come back. I can email Joe while that's going on. So who's next?
I actually don't see Andrea Gallegos on the list either.
All right, who's next?
Well,
We're going through these in a hurry.
Greg and Andy, we did actually encourage people who could not attend to submit 1 or 2 slides if they wish to, and certainly
I see.
if we wanted to look at those, that would be great.
Okay, so shall we go through them then?
Why don't we go through the people that are here first, and then at the end we'll go back, and in case somebody does come in later, or that gives the people who are here who want to speak time, and then we can go through the other ones at the end.
Yeah, very, very smart idea.
I'm going to email them a reminder too.
Okay, then I won't. So, John.
All right. After the Virginia earthquake in 2011, we took a bunch of instruments out and deployed our own network called IDA, which was an acronym for Aftershock Imaging with Dense Arrays. And with just a couple of days' notice, we set out 148 single component stations at a 200 to 400 meter spacing and 33 component stations at a 2 kilometer spacing. The latter were designed to look at amplitude attenuation as a function of distance. But as you see in the picture on the left, the 148 single component stations were a fairly dense array. The scale bar there is only 5 kilometers. And our goal was to actually look at the earthquakes in some detail in the near source region. We were able to put these instruments out in about half a day because we're using controlled source instruments, the Texans in this case. On the upper right-hand side, you can see the largest aftershock we recorded is a magnitude 3.5, and you can see very, very clear PNS waves that are moving out across the array. And if you look at these, they are marginally aliased or unaliased at the dominant frequency of 25 hertz that we're looking at on that image. And in addition to the PNS waves, we can also see converted phases or reflected phases coming in on this image. And colleague Larry Brown at Cornell is actually trying to do some reflection imaging using the P2P reflected phases at this time. On the bottom, you can see, looking at the other end of the amplitude spectrum, that's a magnitude approximately -2 earthquake we're looking at down there. And if we look at the original, or at the pink stations on the map, those are the traditional aftershock network, which is surprisingly dense. And that network was not even capable of seeing whether these are really dense or not. The signal-to-noise ratio on any individual trace is less than 1:1. But because of the correlation from station to station, we're able to clearly see that this is an event. PNS waves are visible, and you can see it moving out across the array, so we know roughly where it is. The point being is that if we have very, very dense networks, we're able to, simply by correlation, reduce our detection thresholds and reduce our imaging and our resolution. And we're imaging earthquakes here, locating earthquakes here down to about a magnitude -1 and with about 100 meters of spatial resolution on the hypocenters without resorting to double difference methods using this data set. Next slide. One of the methods we're using to look at these earthquakes is source back projection, which a couple of other people have already talked about, or reverse time migration if you pose it as a full wavefield problem. We're doing it as a source back projection at this point, where you take the energy that you observe on your array and you back project it to where it came from originally. And on the bottom left-hand corner, you can see the results for that magnitude -2 earthquake. And what you see in the left panel is a map view, and in the center the right two panels are the west-east and south-north depth slices. And I've zoomed right on into the source area, so we're actually looking at the hypocenter here, and you can see a blob of energy occurring at the hypocenter with a spatial resolution of below 1 kilometer, even though that's a magnitude -2 earthquake, and the signal to noise on the actual individual sensors is about 1-to-1 or less than 1-to-1 on most of the stations. Well, it's mostly less than 1-to-1. And on the upper right-hand corner, you can see us doing a source migration or back projection with a magnitude 3.5 earthquake. And on the upper row of images, you can see us imaging the hypocenter with a spatial resolution of somewhere between 200 and 300 meters. And again, as you move down to the next two panels, you can see 50 milliseconds later and 100 milliseconds later, we're actually imaging that source moving in space and time at a scale of hundreds of meters and tens of milliseconds. With images like the one at top, which we're seeing so far, are earthquakes. We've not gone below magnitude 2.2 at this point, but all the ones 2.2 to 3.5, we're seeing the actual propagation of the events. And with these, we can start looking at fault mechanics. And then if you look at just the point sources, for example, the magnitude -2 at left, we can image thousands of earthquakes in the 12 days we had this array out there. And although we haven't done that yet, we're in the process of working on it. And the idea here is that you can start mapping the 4D evolution of stress and strain in the aftershock zone. That's all I was going to say. Thanks. Hello?
That was great. Greg must have stepped off for a moment there. Anybody have any questions? Comments?
This is Greg. I made just very eloquent comments, but I was muted. John?
I was just going to ask, is there anything you saw that surprised? Have you made any observations scientifically that break new ground?
Well, first of all, from just the aftershock locations we're doing, we're seeing some curvature and some details in the fault zone, one of which is that the cloud of seismicity is wider than the spatial resolution of the epicenters, and therefore we believe that that cloud has some real width. We're probably breaking a bunch of little tiny microfaults, not a single fault. And then on the fault propagation, I hate to say it because we're not 100% sure. We're still playing with the resolution here, but I tentatively think we're seeing super shear here.
Ah, good.
Okay, other comments, questions? All right, if not, let's move on. Is it Zhigang next in line? Or?
I did want to point out Joe Fletcher is here now.
Oh, yes.
Yes.
All right, so how do we want to do this? We want to do Joe?
Might as well.
Okay. Joe, you there?
Joe, do you want to unmute yourself? Well, he was there just a second ago.
He's on the list.
He just went live. Yep. Joe, if you want to check your icon, your mic icon on the audio panel, you might have to select a different microphone if you're speaking and we can't hear you. Well, maybe we'll let Joe work on that.
Swami?
Hi.
Hi,
Can
Swami.
everybody hear me?
Hi, Swami.
Hi. Sorry, there's going to be a telemetry because I'm calling from India, so it's going to take some time for the sound waves to reach you. Not really the sound waves, but anyway. So I'm going to tell you about rupture to rafter simulations that we are doing and how these simulations can actually benefit tremendously from full wave field calculations or full wave field recordings. So what you're seeing on the first slide is how we represent the sources. In rupture to rafter simulations, you basically simulate a bunch of earthquakes and you try to answer a question such as what is the probability of collapse of a building or a class of buildings in a city under large earthquakes on a particular fault over the next 30 years. So you're trying to assess the seismic risk, but you're trying to quantify it so that you can make decisions on either where to build, how to improve the buildings, do buildings need retrofit, etc. So you're doing you're making engineering decisions, and these involve probability and these involve uncertainty to be quantified. So we start off with stochastic sources. I'm going to tell you about very briefly about how we do this process of earthquake rupture to rafter simulations. We start out with stochastic sources, and for this we are using a variety of techniques. The first is we're using a bunch of past finite source inversions of past wavefields, and we're trying to characterize the variability of slip from those finite source inversions. We're trying to use laboratory data to characterize the slip velocity. So in other words, Rosakis's group at Caltech does a lot of laboratory earthquake experiments. They measure the slip velocity versus time. You see the function there. And it turns out that they measure it in micrometers per second, and time is microseconds. And if you assume self-similarity between the laboratory earthquakes and the Earth laboratory, then you can make some interesting jumps as to what the slip velocity time function looks like, and use that to characterize slip velocity on faults. In fact, you're seeing on the right-hand side bottom corner, you're seeing a rise time as a function of slip in laboratory earthquakes. And you can use that data, the mean and the uncertainty of that data, as your starting point for your stochastic source models slip velocities. Next slide. So if we generate I haven't told you about rupture velocity, I'll come back to that later, maybe at the end. But once you represent the source this way and you generate a bunch of stochastic sources, you can actually place these source models at different locations. In this case, in this particular case, we are looking at the San Andreas fault and we are looking at the Los Angeles basin. You can place these sources at different locations along the fault and generate, in this particular case, long period seismograms. So why long period? Because that's what the Earth structure allows us to do. It's not resolved well enough for us to propagate seismic waves shorter than maybe 2 seconds or maybe 1 second. So that's a point to remember. When I come back to the final slide, you will see that that's where one of the biggest contributions or benefits that can be derived from full waveform data is to improve that band of being able to predict what the ground motions look like by simply improving the resolution of the Earth model. So here you're seeing a north to south rupture and a south to north rupture of the same source located at Parkfield. It's a magnitude 7.9 earthquake. And then what we will do is we'll simply move, these are the horizontal velocity and displacement maps. We simply move the this particular source along the fault. Next slide. There you go. And as you see, as the source comes closer to the greater Los Angeles metropolitan region, you start to see stronger ground motions, and a shift in so from north to south has the ground motions have shifted. The big patch of ground motion where the strongest motion is now shifted east. In the south to north motions, where the original in the previous slide you saw the source being located far away from the city, the propagation of rupture going from south to north, sending all the directivity, all the energy away from the LA basin. Now you start to see the big patch of slip being closer to the LA basin, and now you start to see the San Fernando Valley lighting up. So, and as you move this source to the right towards Bombay Beach, you will start to see how the ground motions change, their distribution changes in the LA basin. Next slide. So here now you see both north to south and south to north actually causing strong ground motions in the LA basin at different locations. And if you just go on to the next slide, you will start to see that the north to south ground motions now, because the next slide, because the north to south, because the directivity is now directed away from the LA basin, you start to see ground motions in the north to south rupture scenario reducing. And finally, the last source, this is almost like the shakeout scenario, you start to see the south to north rupture actually lighting the LA basin up. So you can do these kinds of simulations with not just a magnitude 8 in this case, but you can actually do this for magnitude 6 to 8. All those earthquakes that would cause any kind of damage to the built up region in LA. Next slide. Before you can do anything else with this, as I said, we need to assign probabilities to each of these events. You've generated a bunch of magnitude 6 to 8 earthquakes. So we use the Uniform California Earthquake Rupture Forecast for this. The more detailed version that's more recently out, but the paper that was based on was published in 2011 by Page and Field. So they divide the entire southern side section of the San Andreas Fault into 7-kilometer segments. So there are 83 such segments leading to 3,403 possible ruptures, out of which the non-zero rate ruptures are only 138. So on the right-hand side, you see the log rate per year for these 138 ruptures. Now these ruptures are based on their discretization of the fault, and they don't have anything to do with our source models, our earthquakes. So what we have to do is we have to take these probabilities and then assign these or spread them out to the ones that we have simulated. And that's what you do, and then you can then specify or estimate what the probability of each of the events that you have generated are. Next slide. You can now place lots of building models. In this particular case, we are looking at tall buildings. You can place tall buildings at every location in Southern California, and under each of those ground motion time histories that you just computed, you can compute what the structural response is. Next slide. And the idea is to get to curves like this that tell you that on the left-hand side you see an older building, the response of an older building, and on the left-hand side you see the response of a newer building, and the right-hand side you see a response of an older building, and at various magnitude levels you see on the y-axis what the performance is. So the numbers may not mean anything to you. All you should look at is perhaps the table at the bottom, that if you're looking at collapse, if you're interested in answering the collapse question, you should be worried about the numbers 0.05. So if you exceed 0.05, if the response exceeds the value of 0.05, then there is a risk for collapse. And you can see that magnitudes anywhere above 7.7 or so start to look bad. First of all, you see greater uncertainty with the ground motions, and hence greater uncertainty or greater spread with the ground motions, and greater uncertainty with the structural response, and as well as risk for collapse going up quite rapidly after 7.6 magnitude earthquake. Next slide. and the idea would be to look at probability of collapse. So all you should be interested in is in the last column, which is listed as CP, which is collapse prevention. And the way to read the table is that given a magnitude 7.9 earthquake, the older building, the first table, the probability of collapse of the older building is about 38%. So if this building is located anywhere in Southern California, the probability that it will collapse in a magnitude 7.9 earthquake in the next, well, given a magnitude 7.9 earthquake is 39%. Then you can combine that information, next slide, with the probability of occurrence of a magnitude 7.9, and in fact you can combine that with the probability of collapse under various magnitude earthquakes and the probabilities of their occurrence to get to this table, which is what we would need to do decision making, which is to say what is the probability of collapse of these two buildings over the next 30 years due to magnitude 6 to 8 earthquakes on the San Andreas Fault. And you see that in the next 30 years, the probability that the older building would collapse in a magnitude 6 to 8 earthquake on the San Andreas Fault is about 6%. Right? So to put this in perspective, a building code, a new building, you design it for to last about 50 to 75 years. And in that time frame, you want the probability of collapse to be as small as possible, and building codes try to limit the probability of collapse to 10%. So the next slide. So this is what we are trying to aim with rupture to rafter simulations. And there are several limitations to these simulations. And most of them have to do with the fact that while we have great computational power, we simply don't have enough data, enough resolution on the data to, number one, to actually understand and be able to simulate a big earthquake. That is, we don't understand the physics of the rupture process well enough. As you see, we are using bits and pieces information from various sources, including laboratory earthquakes, to characterize the slip velocity. So how do we improve that? Well, if we have a full wave field recordings and in particular close to faults, we can change that. We can try to understand the physics of the rupture process far better, characterize these sources much better. Number two, we should be able to then resolve the propagation speeds of waves with periods shorter than 2 seconds. I particularly specifically picked tall buildings because these are fundamental periods in the longer period range, in the 3 seconds, in the 4 second range. And so when you are able to, our Earth models right now, they are able to, credibly propagate seismic waves in the 2 seconds and longer range. They can only be used for credibly looking at tall building responses. But if you're looking at the vast majority of low-rise structures, you simply cannot use these. You have to combine this, and we are doing this. You have to combine this with high-frequency stochastically generated waveforms, which have their own problems. And so the question is, how do we, if we are to design all those nuclear power plants that are going to come up, and we have to do this in a smart way, how do we use simulated ground motion, right, from very large earthquakes, and how can we use that to actually design these nuclear power plants? Right now, there is no answer. But measuring the full wave field is the answer, is in the longer run. Capturing small-scale nonlinear behavior of soils close to the yeah, sorry, this is the last slide.
Yeah, we can't go through it.
Okay.
We really have to.
Okay, I'll wrap up in a second. That is that the other aspect to this is basically simply soils, and that we need to be able to look at soil structure interaction. These become important with shorter buildings. We need to be able to capture the response of buildings because we don't have enough data on that. So all our predictions on structural models are also at questionable, because if we don't know whether we can predict these failures properly or not. And so full wave field measurements, both in the ground, in the soils, in the buildings, is the way to go to be able to do all of these in a sensible way. Thank you. And sorry for going over.
Yeah. So that was the nice ending. Are other people getting this same interference as me? Oh, I just stopped.
I just muted Swami, so it stopped. It appears to be localized to his microphone.
I
So
see.
maybe what we can do is if anybody has a comment or a question, they can weigh in, and then we can unmute Swami if
Okay.
yeah.
All right. So let's operate in that mode. So just a comment. That was a nice overview of sort of some engineering motivation, particularly this last slide, for why dense instrumentation would really help with ground motion prediction and hazard and in this case risk. So the added twist of instrumenting buildings is an important thing to do. So let me open it up to questions from the group.
Am I on?
Yeah.
Greg?
Yes.
Okay. So we put 72 components along with the State Geological Survey into the Rincon apartment condo complex near the Bay Bridge. And it certainly provides a lot of important data for determining things like mode shapes. And Hassan Ulusoy has done a lot of work on trying to determine where you can find damage, both using shear wave propagation up and down the building, using cross-correlation techniques, and using the mode shapes. And both techniques look pretty promising, but they require these really dense arrays.
Okay, so that's a good motivation for dense arrays. Are you modeling 3D modes? Are you doing this empirically, or is it 2D, or what?
We're using ambient noise, so it's using data. It's not a finite element model or anything like that. And we also have one earthquake from geysers that we're looking at.
And do you see torsional modes?
Yes.
Cool.
As well. And you can see, and for a tall building like that, you can see many different modes coming out of the data, like 4 and 5 overtone data.
Nice. Questions or comments about Swami's talk, presentation?
I think obviously this brings a whole nother scale of urban monitoring. If you're talking about large N or wavefields, to be able to get the wavefield through the structure as well, now you're at a single point, basically the footprint of your structure. You're multiplying your number of instruments by another 100, let's say, to take the Rincon as an example. So one of the things I would recommend, at least in terms of IRIS's planning for submitting proposals, is to involve from the beginning the engineering directorate of NSF as well, because I think it'll be important to get them on board if we want to get to this type of improvement in recording the wavefield.
For sure.
Comment, I mean, to me this isn't a huge increase over what we've been talking about, because I presume these can be temporary or limited in spatial extent. I mean, to me, if we have 10 or 100 times the instruments available, we can do these things as well as the things we're already talking about. So I think these are in line with the things we already talked about in terms of requirements for instrumentation.
Okay. All right, so if there are no other questions or comments, thanks, Swami. And maybe, Joe, I think I heard your voice. Are you still on the line?
Yes.
You want to go to your presentation?
Sure. So first of all, I apologize for starting out with more of a hardware slide, but whenever I think about what I can do science-wise, it sort of is colored a little bit by what instrumentation I think I can put out there. So anyway, I thought we had a relative in the UC Berkeley computer science department a little while ago, and in conversations with him, he brought up this concept of smart dust or motes, and it turned out that they had already been thinking about how to sprinkle thousands of components around something like a structure and develop networking mesh technologies to get the data back in real time to some central recording site. So not all systems we might think about are use networking, but what they're doing did. I've seen systems like this being implemented on structures, but not in the same way. So So a dust is really almost like a speck of dust. It's like the size of a grain of rice. And so they really have the idea that they're really small. You don't know, they sort of infer ways of figuring out where they are, and then they talk to each other to get their network data back to some central recording site. And so obviously they'd be very, very cheap. It's not clear what sensors they would use or what battery system or power system they would use. But people have already been thinking about how to do this, for about 10 years now. I think that they, when we started thinking about it, we sort of felt like they would be, could be used for sort of short-term deployments, but typically not very long-term deployments. Certainly, power is going to be an issue. People have tried to take this concept and make it into a piece of hardware. And I mean, when I think the originators thought about this, they thought about coming up with a whole new way of fabricating things. But other people have taken the idea and taken it from a piece of rice to something that's more like a couple inches on a side. And a number of people have done this, like, well, anyway, HP has thought about this as a way of monitoring road traffic, and other people have put arrays on bridges and using this kind of system. But again, things are inches on a side, not the size of a grain of rice. When I started thinking about this in terms of seismology, though, you come down to sort of whether or not we can employ a sensor that's going to really help us perform the kind of seismology we want to perform, so that they're broadband enough or has enough signal to noise over a broad enough band so that we really get the data we want. We're not just recording like a 1-bit A to D on noise or something like that. And so, in the end, we have to, you end up with conversations about telemetry and whether it's star or mesh, but also about exactly what kind of sensor we can deploy and what whether really you're only trying to record the P wave or whether you really need to record the S wave and you need horizontal. So I end up with those kinds of question marks whenever I see this technology. But on the other hand, I really think as a group we should keep track of what these people are doing. Next slide. So the kinds of things that I think about sort of build a lot on the work we did at Parkfield with the UPSAR array, because you can determine a lot from array with being able to say where the particular arrays are coming from, both in terms of depth and azimuth. But the kinds of things we did with UPSAR, you only had one array, and I would certainly advocate being able to deploy like 5 or 6 different arrays like that around some source zone so that you can really have a lot of redundancy in terms of where you think things might be coming from. Back projection, which I think John Hole already talked about, is certainly a system analysis method that a lot of people have thought about over the last few years and think is a better way to go, because I think it has fewer assumptions involved, and the more instruments, the better the back projection gets. And I was very impressed with a lot of the work being done in tomography with the Western United States with a TA array. And one paper by Lynn Rutzweiler and Snyder uses sort of gradient where your the slowness is equal to the gradient of the travel time front. And certainly if you're looking at a map of travel time fronts like Rob Clayton did with the nodal seismic data from Long Beach, you certainly can get a lot more detail about what the gradients are and get a lot more spatial resolution with a really dense array. And then, of course, scattering is something that a lot of people have been interested in. And if you can have a really dense array, you can really start to see the coherence in the scatterers as well. So those are things that I've thought about. Thanks.
Okay, thanks, Joe. So by coherence of scatters, do you mean actually imaging the scattering locations, or
right, trying to figure out where every scatterer is that's contributing to the waveform.
Okay. So questions or comments about Joe's presentation?
This is John Hole. I'll just say that the scattering field, that's exactly what Larry Brown is working with in our Virginia data, is he's actually using the scattered field to image reflectors. He's basically treating it like it's a downhole source, is the earthquake, and a surface array, and can we image where the scatter is coming from.
Okay, other comments? So we got about a half hour left, and I think 2, maybe 3 presentations to go. Andrea just showed up, but who's next on the list? Maybe we should let Andrea set up and go. Is Dave here, Oppenheimer?
I think Jim was going to go for Dave. Is Jim there?
Why don't we go to Jiang? Oh,
okay,
sorry.
I'm here.
Okay.
It took a while to get unmuted. I'm going to violate John's rule and talk about instrumentation a little bit, but I'll keep it mercifully short. We started out about 10 years ago with the idea of trying to more densely record strong motion data in the San Francisco Bay Area, and immediately ran up against a bunch of fiscal limitations. Cost of instrumentation was kind of prohibitive when we started talking about hundreds of instruments, and telemetry is a prohibitive cost that scales with the number of instruments you put out. And the solution that we came up with at that point was Netquakes, which is designed to go into homes and use other people's broadband connections instead of having us pay for it. And it's an instrument which is more narrowly designed than many of the things that are offered by the general seismic instrument manufacturers. So we developed this, put it out for quotes, and is manufactured by Geosig. So they did all the actual instrument production development. We developed, along with this, a data collection model based upon a client-server system, so that the instruments can sit behind a firewall very easily and call in their data when they have something that they want to send, a trigger, for example, or when they do connect, they can accept requests from their on-site buffers. This has turned out to be a very successful way of recording data, and there are currently about 500 of these here in Northern California, Pacific Northwest, Southern California, and elsewhere. The next fiscal challenge that we had to meet was there are several hundred K2s and Etnas operated by the Geological Survey, which are either untelemetered now or on a failing or soon to die dial-up system for returning data, which is expensive and it's going away. So building on the data acquisition system that we built for Netquakes, we are currently building what we're calling Networm, which is a single board computer that we can attach to basically any streaming sensor, and the single board computer is a full-blown earthworm acquisition system. Runs a 2-week ring buffer. We can change that. We can probably blow it out to half a year or a year ring buffer. Again, the same model. It calls in only when it has something to say or to see if it is being requested data. And by doing this, we're trimming our telemetry costs by almost an order of magnitude. And we're very sensitive to this because over the long term, telemetry costs will kill you. So we're currently doing this, and so basically the fundamental software is developed, and then the next step, which we have not gone to, is carrying this one step further, not using it as a system to retrofit existing data loggers, but go ahead and find an appropriate data or sensor that could be used with an off-the-shelf single board computer to produce a very low-cost device that only needs an internet connection. And this is sort of where we are currently headed. We don't currently have the funding to develop this, but this is sort of where we want to go. There are a lot of numbers and details on the slides that I won't bother going into. And why don't we skip to the second slide? Again, where we are headed is a further simplification of this whole system. I think that's probably about all I really want to say right at this point.
Okay, thanks, Jim. So when you say a further simplification of the system, can you just elaborate a bit on that?
Well, the current operational system that we have is designed primarily to retrofit the existing data loggers telemetry systems. So we are using we are connecting them to K2s, Aetnas, RT-130s, and using all of that very expensive front end for the actual sensing of the data. The next step, as we see it, is moving on to a lower cost standalone sensor system. Some which have been investigated have been the Fidget system, ONAVI, and some of these they're coming very close to being acceptable sensors.
Okay, thanks. And just to be clear, this is trigger data, not continuous.
It is triggered data, but it is accumulating a continuous record at the local device. So if we have a supporting regional array that is already detecting events, data requests can be made, it can be retrieved.
Okay. Questions or comments? No? All right, in that case, thanks, Jim, and let's move on to whoever's next. Who's next on your Jigan? You there?
Yep, can you hear me?
Yep.
Okay, yeah, this is Jigan Pen from Georgia Tech. So I'll come back to science a little bit, but except I won't have too much, result to show you, except to tell you some ideas that we'd like to explore by putting this dense array. Well, this slide basically shows you some previous studies we have been doing by imaging photon structures with dense array. In this case, this is the example that was placed across the rupture zones of the 1992 Landers earthquake. And as you can see, the station there, especially right around the rupture zone, is pretty dense, about 10 to 20 meters within the fault zone, and then increase to about 50 to 100 meters outside the fault zone. And by doing this, we can record, seismic waves that are sort of like bouncing back and forth inside the damage zone, which we sometimes call it fault zone trap wave. This has been a topic of studies by many others. Some of them are already participating in this, workshop right now. So basically, the benefit of those dense arrays is, of course, you can, see how the waveforms change across, a few tens of meters. Unfortunately, the way that has been deployed before is mostly deployed in single lines or a few lines because of the limit of instrumentation. So next slide. So the next slide, what you will see is basically the same image of the Long Beach 3D survey that Rob talked at the beginning. And this is basically our initial attempt of looking at the same data set of an event that occurred just slightly to the left of the dense array. And basically you can see as the event propagates across the network, of course, the stations on the north side of the Newport Inglewood Ford, record waveforms that propagate faster than the stations on the south side. Now, in addition to that, if you cut a slice across the dashed line and look at the waveforms, you can see very nice coherent waveforms, not only showing the different speed across the network, but there are also some additional waveforms that are recorded at stations south on the so-called slow side. Looks like those waveforms are probably some sort of reflected waves that could be associated with the Newport Inglewood Ford as well. So we just started, looking at the data not too long ago, so we don't have any result yet. But this is hopefully some slides just to show that what we can achieve by coming up with a detailed photon imaging studies using those 3D dense array. So I guess I'll stop here.
Okay, thank you, Zhigang. So questions or comments on Zhigang's presentation? It's impressive how much interest this nodal seismic experiment has gained. To me, it just speaks to the promise of dense recording.
Yeah, absolutely. I think there are, in addition to this, I'm sure there are many other interesting studies that people can come up. So this clearly shows, is a good case of showing how, how much we can do with such impressive data set.
Yeah. Anyone else? All right, well, thank you. So Andrea's here on the call.
She is. Her microphone is unmuted. I didn't have a chance to do a check with her beforehand, but Andrea, if you're having, we're not hearing you right now, but if you click on the little mic icon on your audio tab on the GoToMeeting panel, you might be able to select one that will work. Yeah, I see you muted and unmuted. That's if you click on your it's a tab called audio, and that may give you more than one option. Just trying to work this out with Andrea in the chat box.
Okay, well, maybe we can, while you're working that out, maybe we can open up. There are a number of people on the call who haven't presented anything or had a chance to speak up or chosen to speak up. So anybody want to weigh in on their thoughts about this, recommendations perhaps?
Oh, well, I'll offer a quick remark if there's time. Just kind of an ad that we're doing an experiment on St. Helens in the next year or two, IMUSH. It's going to take a couple thousand of the sensors put out along the roads by Alan Levander, and so we're really interested in looking at volcanoes with these large number of receivers type experiments. So that's all I wanted to mention.
Okay, super. And I think, John, correct me if I'm wrong, but I think there's going to be a group focused on volcanoes. Is that right?
That is correct. I'm trying to remember who's going to be leading that one. Seth Moran is going to be leading that one.
Oh, and Seth's on our IMUSH experiment too, so he'll represent our interests.
Yeah, we're hoping probably in late May for that one, but we still haven't set a date yet.
Mm-hmm.
Okay.
So this is Richard Allen. If there's time, I kind of have an observation or a comment that I don't know if it's helpful or not, and this is not meant to be a negative comment, but I sort of feel like, as many people on the call know, I also have a lot of interest in these very dense arrays, but I think what we're not doing a particularly good job of doing is motivating the science behind some of these arrays that we're putting out. And so the question of what's the science behind some of this has come up a little bit, but I think as a community, as a group, we would be well served if we could try and flesh out these science objectives a little better. Often, we have to think about the technology, and we spend a lot of time thinking about the technology and talking about the technology. I think it would be helpful if we could do a better job on the science side.
Yeah, I agree. I think it's essential, and so that was supposed to be the focus of the call, and we've drifted a bit at times, but yeah, the science, this is contributing to a white paper, and the science absolutely has to be featured in that. And so, this call is part of getting input for that, but it's not the only thing. So
I think this is Herman Prieto from MIT. I think one of the maybe features that we're missing is the really high frequencies that we ought to be able to extract from the data. And no matter how dense we make the arrays, we're never going to be able to get unaliased, spatially unaliased high frequencies. But what we ought to be able to do is to be able to describe the sources, maybe the high frequency radiation of the sources. High frequencies now I'm talking about 10 to 100 hertz. That is very important for tremor, for general seismicity, microseismicity with these dense arrays. And we have to figure out a way of getting maybe the frequency content of the signal, not the phase, but the frequency content of the signal in the right way, so that we can really see how energy is being radiated at the high frequencies for this tremor, microseismicity, small events, because this is the piece of information that we've been missing for many years, forever. If we can't do that with dense arrays, then there's no more. We have to be careful with that. We need to be able to do that. Getting the high frequencies, how it's being radiated, because that will tell us about the rupture process itself. At least a big component of it. Obviously, the rupture velocity that we can get with back projection is very important, but that is still at lower frequencies that what we could potentially get.
So Herman, when you're talking about high frequencies, what's high? 5 hertz and higher?
10 hertz and higher, something like that. I mean, if the corner frequencies of the tremor is in the 5 hertz, and we
There are 21 other callers on the call. There are 21 other callers on the call.
That we could have easily migrated twice that, because the velocity model there is fairly well controlled. We could have migrated considerably higher frequencies than that. So that was 100 sample per second data, and we were migrating right up to that.
Yeah, no, that was really impressive, actually. What I think, and maybe John Virali was asking whether the 1D, the line array, a denser 1D array would be better than a spatial array. I think that's very important that we show whether simple line arrays are better. I'm guessing a 2D array is much better, but we have to be careful how we pass the data to get to the high frequencies.
Yep.
Well, and just another comment. I mean, to me, the real prize in this all would be if we could catch a big earthquake with this dense array. And I'm not at all sure exactly what we can resolve, given the difficulty of unscrambling signals from a lot of parts of the fault all at once. And we don't even know how complicated the rupture will be when we can see it. But that, I mean, should be a goal. I'm not even sure how to approach guessing what it is we'd see if we had such a recording.
That's a good point. I would, sorry, can I?
Sure.
So the other piece that we might be missing there is using multiple arrays. If you look at recent papers from back projection, they always back project North American arrays, Japanese data, or European data independently. They can't somehow, I'm guessing they are not good at combining the three data sets in one to get one single image out of all the data. And that might be one step to go that we need to figure out how to do.
Yeah, I agree. Yeah. So responding to John's comment about not being sure what we'd see if we had a dense recording in close to a large earthquake, I think you're right, and I think that's really interesting, and it's really important because those sorts of some sorts of assumptions are used for how ground motion varies in close to big earthquakes. There's very little data, and if we had dense recordings, we'd have at least empirical constraints on one realization of how ground motion behaves with distance in close to big earthquakes and just how variable it is. Right now, we're just really guessing.
So with the park field data, when we use the UPSAR array to image or not image, but track the rupture front, once we got past the initial start of the S wave, we would get one very strong peak in our slowness space plots that represented the movement of the S wave down, the source of the S wave down the fault. But right around the S wave where it started, we could see multiple peaks. And so at one point I went back and tried to pick every peak out of the slowness space plots and plot them on some sort of, azimuth or depth plot to see how many different, if there was a correlation between some of these other peaks that were showing up. So one way to approach finding out what different parts of the fault are radiating at once is using dense arrays and looking for these different arrivals coming in at the same time.
Right. So remind me, how many elements were in the UPSAR array? It was a dozen or so?
Between 12 and 14 stations.
Yeah, so pretty sparse array.
Right.
But still quite interesting.
About 800 meters.
Mm-hmm.
Maximum dimension.
Oh, and just to follow up on Greg's comment, I mean, I think I agree that looking at the distribution of motion and how that relates to our attenuation curves would be very enlightening. But I guess to me it's most interesting trying to tell what's happening right on the fault plane or whatever volume is radiating, or even maybe the near surface by the stations complicating the picture. So looking at where the energy is being generated would be great. But as everybody on the call knows, between looking for a source in 3D with time as an extra dimension and focal mechanism as another wild card, it could be we just can't unscramble what's happening at the source, even with perfect data at the surface.
Well, it's an underdetermined problem, so at some level we won't be able to know everything, but even with spatially continuous recording, but we'd learn a lot about the source itself and be able to constrain a lot for sure.
Yeah, definitely.
I have a
so
question.
I don't disagree with a word you said.
Can I ask?
Yeah.
Hello?
Yes.
Yeah. So the question is the following. So as we move, or we discuss very dense arrays, how do the methods change? Because it seems that right now, if you collect, let's say, 50 to 100 station data, you process every sensor. But if you have thousands of nodes, and the method's probably going to change. You maybe don't need to use every sensor, but every, I don't know, second, every third sensor, because it might be, different totally rules in the game now. You're talking about really big numbers. I mean, how does the approach changes processing the really data sets collected from the dense networks versus the more sparse arrays, where you can process basically every sensor, and you allow to do this in terms of the technology and the methods and current thinking. That's
that's a very good point. I think it has the potential to change everything in the way, almost everything in the way we detect earthquakes, locate them, characterize them, and we're going to, this is the world of big data. We're going to have to get serious about data-intensive computing, and that goes all the way from how we store the data, such that we're not I/O bound when we're processing it, to how we take advantage of all these extra channels.
Right. Well, that was basically half of the question. The second one is, do we have students, prepared to do this? Because if you take an average student in seismology, they might not have enough background to deal with those humongous arrays, because they still look probably at the data as a classic, data that collected from 50 stations, but not from those very dense arrays. We might need to think about a proper preparation of students, and what classes are taught to seismology students in terms of statistics maybe, and some other disciplines that would allow you to help to process this data. Because if you just stick with the classic approaches, you might not achieve what otherwise could be achieved.
I agree completely. So we should all, and so our students benefit to learn how to do this kind of thing, and we should be embracing it because it's the future.
I nominate Igor to write the workforce training portion of the proposal.
To follow on, to follow on those comments, a student of mine is working on full wave reverse time migration, and started to play with a couple of hundred sensors and up to 1,000 sensors, and shows a tremendous improvement with 1,000 sensors relative to 100. So those kind of the dense array.
Yeah, so the students who get out in front of the wave are going to have a big advantage over those who don't.
I just wanted to break in and mention that Andrea, I think we have her audio situation worked out if we still want to have her slides presented.
If you want.
Sure, why don't you go for it? We have 5 minutes left on the call, so.
Yeah, time zones messed me up, so I was really sorry I barely came in now. I don't really have a whole lot to say. I'm just a student, but we are interested in definitely looking into full Wavefield seismic data, mostly because we're currently looking at LG attenuation and the simplifications that we're making in order to come up with these Q maps are they're pretty simplified, especially for a wave like LG. So what we really want to do, what we really see being a good thing about the full wave field inversion is that we'd actually be able to get the true ray path of the wave, because right now we're treating it almost like a direct S wave. And that's obviously wrong. And so with something as complicated as the LG phase, we would really like to be able to come down to what its true nature is, so we could get a much better idea of what the actual absolute value of Q is. Because the patterns right now are pretty well determined, but the absolute value of Q is pretty uncertain. So that's kind of what my group is thinking about when we're looking at full Wavefield seismic data. We haven't worked with it yet, but I would definitely like to. I definitely think there's an interest in it, and like people are previously saying, it's kind of the forefront of what seismology can do now that we have these large, dense networks. And it would it'd be important for ground motion predictions and various other tomographic models and things like that. So that's about all I really had to say. So.
Okay. Thanks. So concluding remarks on this call?
Just to talk about something that's sort of pie in the sky. What if we had an INSAR satellite sitting off the west coast in a geostationary orbit, snapping pictures 10 times a second? I mean, would that give us special resolution that's just way beyond what you could do with any array of seismometers?
What's the sensitivity?
I don't know, but it seems like you can get sort of instant XY coverage on a plane on the Earth without moving anything, you know, in terms of seismometer arrays or anything. So I was just wondering if you have an extra $100 million or something, you know, would an INSAR satellite solve some of the problems that we might be facing with a really dense array?
Well, that's a big topic. You know, I think, so the current INSAR satellites, I believe they're the sort of amplitudes they can measure are millimeters, so that would only be relevant for, you know, substantial earthquakes that you would be able to image wave fields. There'd be problems with cloud cover and whatnot, but yeah, it's a big topic. Interesting idea.
This is Gampen. I have a question, a follow-up with previous topics about capturing big earthquake. I guess here we're talking about a dense array is more like a 4 or 5 hertz geophone. So in that case, will those sensors be saturated if we're waiting? Our purpose is to wait to capture big earthquake, and so I don't know if that's would be relevant to when we're writing things up. Whether we're primarily focused on waiting for big earthquake or just record, putting the sensor somewhere of interest and record for a long period of time, and then analyze, probably mostly microseismic or even ambient noise.
So I think the off-the-shelf high-frequency velocity transducers will be off-scale in close to a big earthquake.
They'll be off-scale with a bit of magnitude 2 if you're near the source, based on our Virginia experience.
Okay. So we're biggest.
That's within kilometers of the source.
Yeah.
So yes, this is one of the things that the large N needs to discuss is, what is the sensitivity and can it be changed depending on what your deployment is. The different instruments will have different sensitivities, and that's a critical question. Similar with frequency response.
Yep.
This is Jamie. One last comment on things we haven't really talked about, but that may become important, is fiber optic sensing technology and the ability to use basically a continuous wave field coming back from a scattering on the fiber, where you can actually have infinite resolution, or maybe not infinite, but you can take points all along the fiber, and that could be deployed in, not just a line, but an array configuration as well. And there's a lot of work being done on that now, and I was surprised nobody submitted slides on that, but I think that's something to consider because it gets to big data, large N, and full wave field.
Yeah, okay, so that's an important point, and I guess maybe this is a good way to wrap up. But what Jamie points out is there are technologies that are coming in the pipeline, and for the seismological community, for IRIS, this is sort of like buying a camera, right? The technology keeps changing, and 3-year-old camera is out of date. So I think that's a motivation for focusing on the scientific objectives in this white paper, and making some commitments to certain technologies for the initial go at large N, but keeping in mind long term that this is going to be a continuous process in terms of technology. All right. So with that, I guess, unless someone has something else they'd like to say, I'd like to thank everybody for their participation. I'd like to emphasize that we're open to your feedback and input, and as well as input from others who couldn't make this call over the next month or so, and that we'll be working with John to develop a component of the white paper that represents the interests that we heard about today.
Yes, I would strongly encourage people to follow up with extra materials that you think we might have missed, as well as with technical specs that you think are essential to providing the particular scientific needs.
And I'd like to thank everybody for observing good meeting practices. This went very smoothly.
Yes, I agree. Good job. And thanks for facilitating it.
No problem. And if anybody has any comments about things that we could tweak to make this a little smoother, please send those to me. I'd love to hear them.
Okay, I think we're the first ones to do this. Is that right?
That's right. This was the pilot episode.
The guinea pig, as it used to be called.
That's right.
All right.
And I'll remind everyone here, I'll have this recording posted in the next day or so on the Wavefields website, and I'll send a note out about that.
Thanks to Greg and Jamie for organizing it.
All right, thank you.
Thanks, everyone.
Thank you all.